My friends, today I'm going to explain the application of Schrodinger equation for one-dimensional square well potential. This is our square well potential. The x is starting from this point. So we call it x equals to 0. And here x is equals to L, mean width of the well is capital L. Now what is the depth of the well? It is measured in terms of the potential energy. And potential energy is minus V naught. Potential energy is negative, minus V naught, I have divided this problem into the three regions. Region 1 is here to the left side of this square well potential. Region 2, which is itself a square well, and region 3 to the right of the square well. So potential equal to 0 when the x is less than 0, mean left hand side. Potential is minus V naught inside the well, and to the right of the well potential is again 0. For example, if the potential energy is minus 50 electron volt, mean depth of the well potential, let it is minus 50 electron volt, and a particle is inside having total energy minus 30 electron volt, then what will be the kinetic energy? Very simple. Kinetic energy will be simply 50 minus 30, 20 electron volt. Mean this is the kinetic energy, which is always positive. If you add this energy in the potential energy minus 50, it becomes minus 30, which is the total energy. Total energy is kinetic plus potential, which is total energy is also negative. If the total energy is negative, that means any particle which is inside the well will remain bound with the well potential. Particle remain inside the square well potential, that is remain bound within the potential, it cannot escape. If the potential well disappears mean V naught becomes equals to 0. Then what happen? Kinetic energy becomes equals to the total energy, which is negative minus 30 electron volt. The kinetic energy cannot be negative. So, the particle cannot escape from the potential well according to the classical physics. This according to the classical viewpoint. Potential energy is negative minus 50, total energy is minus 30, kinetic energy is 20 inside the well. But if the well, if the potential becomes 0, like to the left side or to the right side of the well, then if the potential becomes 0, the kinetic energy comes out to be negative, mean negative of the total energy. It is not possible. So classical physics says any particle cannot come out from the well. So what happened? Particle bounces back and forth only and remain inside the well. Now I'm coming to the quantum interpretation. I'm uh, I'm writing time independent Schrödinger equation. Time independent means only the Schrödinger equation, the wave function, it is a function of the position or the distance only. So this is the Schrödinger equation, time independent. Now in the region 1, there is no potential energy. So writing here, the potential energy is 0. And we are writing psi as psi1. And total energy is also negative. So the formula becomes, I substituted E as minus E dash and potential 0 in the region number 1. And psi is a wave function in region 1. Psi 1, I'm talking psi 1 for region number 1. So let the substitution is, you call 2m upon h cross square E dash as k1 square. Any constant k1, where k1 is the root of this vector. So the Schrödinger equation becomes like this. Now what about the general solution of this equation? Psi 1 equals to a e raised to power minus k1x, b e raised to power k1x. Now there is a property of the well-defined wave function. This is a very important property of any valid wave function, well-defined wave function. It is one which should approach 0 when x tends to infinity or minus infinity. Now in our case, because we're discussing the left hand side of the well and x is equals to 0 here, you can approach only x to minus infinity. Okay, so not plus infinity, which is the region number 3. So x can approach to minus infinity in region number 1. So if I substitute this infinity here, what happens? This factor tends to infinity, but this factor tends to 0, because e raised to power infinity is infinity. As it approaches to 0, so this is good, and it is according to the well-defined wave function. Okay, and as this tends to infinity, so we are not taking into account of this factor. So a is 0. So this becomes the equation. Only one factor psi 1 equals to b e raised to power k1x. Now in region number 2. In region 2, potential energy is minus V naught and E is minus E dash. Substituting in the Schrödinger equation, V as minus V naught and E as minus E dash. And psi written as psi 2. Now let taken as constant K2. I'm taking this as factor K2 square. Okay. What is K2? K2 is the root of. So this is our K2. Now general solution of this equation, psi 2. The two other constants, arbitrary constants C and D. Now coming to the region number 3. So again here the equation becomes same as that was in the region number 1. Same constant K1. Psi 3 is also well-defined function. Now writing the general solution. Now here arbitrary constants are F and G. one thing you keep in mind, in region 1 and in region 3, there is no iota in the solution. Iota was only in the region number 2, which is the square well potential itself. Now there is a very small question for you, very simple. Why why we why we have chosen iota in the general solution in the square well potential but no iota in region 1 and region 3. Again, psi 3 is well defined function. So x, because it is the right hand side, region 3, and in region 3 x tends to infinity. So f e raised to power minus k1x mean it is in the denominator 1 upon e raised to power k1x, and x tends to infinity. So this factor goes to 0, and this factor goes to infinity. Well defined function is that which tends to 0 when x tends to infinity. So f is okay. So psi 3 becomes f e raised to power minus k1x. Now we are coming the boundary conditions. Okay, the wave function is continuous at the boundary at x equals to 0. So psi 1 and psi 2 are equals at x equals to 0. Now psi 1 was and psi 2 was. Substituting the x equals to 0 here, we'll get b equals to c plus d. Wave function should be continuous at x equals to L also. Now writing psi 2 and psi 3 again and substituting x equals to L here and equating the two. Equating the two. So this is equation number 10. Now because the wave function is continuous, so that derivative also equals at x equals to 0 and x equals to L. So derivatives are also equal. So first of all, writing equation 5 for psi 1. Now writing equation for psi 2. Previously I derived, just see. And now taking the derivatives of psi 1 and psi 2. Taking the derivatives and equating the two derivatives. Okay. So at x equals to 0, we are equating. The equation reduces to. So because they are equal, derivatives are equal, this is equals to this one. So it's very important equation. Equation 11. You number the equation as 11. Now equation 11 was, you find c minus d from here. And iota taken in the numerator becomes minus iota. So this is equation 12. Now derivative also equal at x equals to L. Psi 2 was equation 7. And taking derivative, very simple. So substituting x equals to L here in the equation. Now psi 3 was taking its derivative also. There is no iota, remember. Two derivatives are equal at x equals to L. So these two yellow circles are equal. Okay. Now dividing by iota K2, the equation becomes I think a rest part of this article is just a simplification of finding the value of some constants in order to know what about the energy situation, energy values in the potential well. Okay, you go on simplifying. If you come across any difficulty, write me in the comments box. Okay, thank you.